have a video already talking about the Mohr-Coulomb failure criteria and how we use it when we apply it with compressive stress exclusively. But there's another important fact to consider, and that's that a lot of times when we have a confined specimen, the failure mode is not compression, it's along a shear plane, along some internal fracture plane within the specimen. So this video is going to be dedicated a little bit more so to the shear failure envelope, which is a subset of the Mohr-Coulomb. Now, to give you the rundown, the review, Mohr-Coulomb or MC failure criteria is very nice. It's very nice because it's linear. Linear, of course, mathematically makes us breathe a bit of a sigh of relief. It's easy to set up, it's easy to use, it's easy to understand. It can be done completely analytically, no need for any numerical stuff going on. So it's linear, that's nice. It's a way of estimating rock strength. And in light of my previous video, I will highlight that rock strength as opposed to rock mass strength. Of course, when we talk about rock, we're talking about a laboratory setting. We're talking about testing that we can do over numerous trials and produce some results that we can use in a semi-scientific and predictable way, right? Rock strength instead of rock mass strength. And it is used to predict the strength of rock, the compressive strength of that rock with changing confinement. And when we talk about confinement, we're talking about that pressure, right, that's applied around any rock that isn't in that principal direction, right? When we think of the principal direction, we're thinking of maybe the vertical stress from the weight of the rock, and then the confining stress or pressure is everything that's surrounding it, right? And to illustrate that, right, we could do it in one of two ways. First, kind of the hand-wavy theoretical way would be a little stress element, right? And you could say, yeah, maybe vertically we've got our major principal stress, sigma 1, right? And then in the other direction, perpendicular to that, we have a sigma 3. And then sigma 2 would be, the one that's in between the two that's maybe acting into the page in that third direction, right? Still perpendicular to both of them. And then, of course, that that's not always the full picture. If we start altering sigma 1 and sigma 3 such that they are no longer principal stresses, then what do we induce? We induce shear stresses. So again, these do not exist when it's just sigma 1 and sigma 3, the principles, but they will come into play. And that's why we need to analyze the shear component as well. To draw this picture in a more practical sense, this is what you'd see in a laboratory. What you'd see in the field in situ is going to be different again, but for laboratory testing, this illustration works quite nicely. You'll have a core, a cylinder of rock that's been cut, ground, dried, all of this to specific specifications that are going to allow us to keep the results uniform, predictable, limit the amount of variability. You'll have sigma 1, that's for a uniaxial compressive strength test, and then when you go into a TCS, triaxial, right, you'll have some sigma 3. And this isn't just applied, like in one plane. You'll have it around the entire circumference of the cylinder. I'll just draw it like that to simplify it. But this in a TCS cell would usually be from a sleeve that will contain, an oil or some fluid that you can increase the hydraulic pressure of to apply, again, that confinement around it. So, of course, to detail, whoa, that's we can do better than that. We can do better than that line right here. To illustrate this point, the results that you would obtain from a lab when you're talking about the Mohr-Coulomb failure criteria, what does that look like? And this should be review from the other video, but again, just to kind of keep everything squared away here, you'll have on the x-axis, you'll have your sigma 3, right? We increase the confinement and see what kind of effects that has on the strength. And then here you'll have sigma 1, right? That principal stress, and we'll put as an additional subscript F, indicating that this is the maximum principal stress when it failed, right? And so you go through and you'd start collecting data. You'd start with a UCS, uniaxial compressive strength test, right? it's only loaded in that one direction, and that's going to be your y-intercept, right? We have 0 sigma 3, 0 confinement. So UCS is going to be our y-intercept, uniaxial compressive strength. And then at certain intervals, we're just going to increase that sigma 3 and continue to plot these points. And what it usually will look like might be something like this. And the Mohr-Coulomb failure criteria says that we can stick a linear, just a line through those, right? And make a function out of it, a function that we can use for modeling and predicting the stress or the strength and whether or not a certain rock will fail under given conditions, right? Under given loading. And of course, that equation, if we look at this, we're linear, of course. So we're going to have our dependent variable, our sigma 1f. We'll say sigma 1f is equal to, what is it equal to? We have the y-intercept, the UCS. That would be the b in our y equals mx plus b, right? And then plus something times sigma 3. So we'll have sigma 3, and then the slope of this line is what's going to be important, right? So if you were to try to determine the overall slope, right, you would draw this out as a right triangle. You would have the change in sigma 3 over the course of all the experiments, and then the rise here would be the change in sigma 1f over all of the experiments. So empirically, what we would call this value would be, that would be the rise over run, so that would be, we'll just write it as delta. We won't write the subtractions out. We'll say delta sigma 1f over delta sigma 3, which will just be the final sigma 3 you calculate minus 0. And we call that property, we call that beta, right? So thinking about it on that graph, right, that's going to be your little triangle, your little slope, that's going to be beta. And beta is the strengthening parameter. So we put that in there. Okay, and then really the practical implication of this, if we clean this up a little bit, you would say that anything below this line we are predicting to be safe. And we could calculate a safety factor by taking, if we know that if we have a point here, right, say that's the point we're analyzing, then we look at basically the ratio between the sigma 1f we have here, or the sigma 1 we have here, and the sigma 1 at failure, the sigma 1 that would be expected at failure up here, right? So looking at this picture here, again, not to know numbers or anything associated with, but that's a safety factor, maybe 2.5, somewhere between 2 and 3 it looks like. Nice. Okay. And then, of course, anything above here we are saying will fail by our model. Not good, not good. And of course, as we collect more and more data, right, you might start seeing it speckle itself around here, maybe, keep in mind that every single data point there is a test, which requires the rock, it requires the instrument to be used, it requires the people to operate it. So it's a lot of time and money. So maybe this much data isn't even practical. But if you do have this much, then, you can make it a little bit more conservative. Maybe say this green line now, it looks more like this, right? It's still a straight line, but you've adjusted it such that it tries to include as many points as possible in that failure region where we know failure actually occurred. And that's just a method of building confidence that you factor into your strength assessment, which you would then factor into a rock mass classification, right? Ultimately, all of this is for, again, it's for rock strength, and rock strength itself is only a small component of rock mass quality. Okay, that's about all I've got to say about the compressive strength, and using that, we'll kind of launch pad into talking about the shear component, right? So we've gone from talking about the compressive stress failure envelope to a shear stress failure envelope. And to do that, we'll look at this guy again, and just as a reminder, remember we have a sigma 1 being applied straight down in that TCS, and then we'll also have our sigma 3. And remember, we have no shear stresses being applied in this laboratory setup, or very little in any case. And since there's no shear stress, we know that these are indeed principal stresses. And when we talk about principal stresses, remember, as they pertain to stress transformations and Mohr's circle, we can draw those out. And if you're not super comfortable with Mohr's circles, I really would recommend, it'll make this a lot easier. I've got a video on them. You can find them all over YouTube, Mohr's circle. Just the basic explanation. You don't need to get into the whole derivation, but, the mathematical implications and how to effectively use one is what we're going to be doing here. But you'll have a Mohr's circle, and, right, we'll draw these as full-on axes, I guess. This will be your sigma, and this will be your tau, right? Normal and shear stresses. And what we have right here is sigma 1. That's our major principal stress, and sigma 3 is over here, right? And remember, at those points, there's no shear stress. But as you change the orientation, this is the important thing. When we look at this data up here, we're thinking of it, it's a little bit limiting, and it doesn't keep your brain thinking about it in a very realistic way if you're just thinking about it in terms of principal stresses, because so many times what you have is them changing and reorienting themselves around discontinuities, around fracture planes within a rock or rock mass especially, right? And this, of course, is extremely relevant in rock mechanics, but take any engineering discipline, right? The same kind of principles that apply to stress here are the same principles that apply for stress in a rotating shaft, in gears in a gearbox, all these mechanical components in a column of concrete, in the I-beams that are used in civil design, right? All of these things, these stress and strain basics are so fundamental that they really will do you a lot of good, no matter what you're doing, to internalize, right? So the point is, once we're able to think about rotating these axes, right, we're going to start changing it, right? Say, all of a sudden, instead of being right along the x-axis there, all of a sudden we've rotated a little bit. The maximum normal stresses we've incurred have decreased, but all of a sudden we're experiencing some shear. And what if the rock is weaker in shear than it is in compression? And in fact, what we find most of the time is that rocks in confinement are failing along shear planes, right? So this is where it gets relevant, because up here at the top of the Mohr circle, you'll know this is where we have tau max. And of course, it's symmetrical about the x-axis, so you'll have another tau max here, just in the opposite direction, right? The magnitudes are going to be exactly the same. So that's important. What is that tau doing? Well, let's bring a picture over here, and this is going to be a plot that is derived from the results of the previous plot we made. We'll still have zeros here, and our x-axis will be sigma. That's all sigmas, not sigma 1 or sigma 3 exclusively this time. All sigmas, just like it is for the Mohr circle. And then up here we'll have our taus, right? And what we're really going to do here is for every single point up here that we plotted, we're going to have a Mohr's circle. So when we were going through this at first, we were taking a single sigma 3 and associating it with a single sigma 1f. What we have to do now is draw a Mohr's circle and find taus on them. So it gets a little more complicated, but you'll find that the result is still very nice. It's still a linear approximation. So let's just start drawing, and hopefully it'll start clicking. Oh, and you'll notice I'm just doing one quadrant here. It keeps it a little bit cleaner. We don't need to show the reflected, the symmetrical portion below the x-axis, and we'll say that everything's in compression, which is positive in rock mechanics, so we won't concern ourselves with what's to the left of the tau axis either. So to start off drawing these, we'll say that we have this point here. This is the very first test that we ran where we were in uniaxial compression, where we said that sigma 3, the confinement, was 0, right? So there's our sigma 3. We'll call that sigma 3 1. 1 for the first test we ran, right? Sigma 3 1 is 0, uniaxial compression. And then over here, it had some associated sigma 1f, right? So we'll call that sigma 1f1, the failure stress at that first experiment we ran. And of course, this is the diameter of the Mohr's circle right here, so we can draw a Mohr's circle around it. And it's going to go up to some height that is going to be equal to the radius of the Mohr's circle, which is the average of these two divided by 2, the difference between these two divided by 2. And that is going to be on the y-axis, or the tau axis, are tau max 1, right? So, okay, we have a tau max, and really, if we're saying that most samples fail in shear, then this is an important number. This is really telling us what we can expect to be what's causing us trouble. Now I'm going to continue drawing more of these. Let's say we increase. I won't label them, just know that these were for the first experiment, and that they'll go on subsequently to trial 2, 3, 4, etc. So we go on and draw, maybe it goes a little bit more out like that. And we have a circle just like that. Rather artistically liberal definition of circle there, but bear with me. And you'll just keep doing them. And what you'll see is that generally, experimentally, these humps will continue to grow. Space them out little by little. And these circles get bigger and bigger. And I'll do one more here. And again, it's not the cleanest. Well, that should be... Did I grab the... No, I grabbed the right point there. Let's make that a little taller. There we go. That's more of a hump than a circle, but we're not here to rip apart the drawing. Just know that each of these, at the top of each of these circles, right, is a tau max. Right there, right there, right there, right there. And just like before, just like with the compressive stress where we said, okay, we can draw a linear approximation through this empirical data, we can do the exact same thing, trying to make it roughly tangent to these points, trying to get it to include all the points on these circles, right, and estimate what the failure criterion is for this data, right? And so really what we can do, again, is just write out a linear approximation, a model for this data, completely empirical. And again, Mohr-Coulomb, always linear, so this will be a simple linear thing. Instead of looking at sigma 1, though, now we're using tau, and this will be our tau, the shear stress that we can allow before it fails, right? So we'll call that tau F, if you will. And now if we look at this, what we have, there's going to be some y-intercept that I'll get into in a little bit. Let's actually focus on what's going on in between here first, right? We're going to have some, first the independent variable. Let's discuss that. We have sigma 3 and sigma 1 on the x-axis now. So what's usually going to be easiest for us is to just take each of these tau maxes, right, is sitting directly above on the Mohr's circle. I'll draw it on this one that actually looks like a nice circle, right? If you draw this down, what you see is, again, it's that sigma sub m, or sigma mean. The mean value of the stresses, right, is where tau max is going to occur. And sigma m, what it's equal to, of course, is just the arithmetic average of these two numbers. So that's going to be sigma 1 plus sigma 3 divided by 2. Okay, so we have a new number that's a product of these other two numbers. I'll just plug sigma m in here. So we'll call this something times sigma m, right? And when we talk about what that something is, well, it's the slope of this line again. And just like we did with beta up there, we can call it something. But in this case, there's a very specific thing that we call that. So instead of calling it beta, we're actually going to use a tangent, right? And just to make sure you're with me here, right? If we blow this out, we have a triangle here, right? We have some angle that we'll call phi, and then we have a rise and a run, call the y there and x here. And then you know that tangent SOHCAHTOA, right? The tangent of phi, this angle, is going to be equal to that opposite over the adjacent, right? Just basic trigonometry. Y over x, or in our case, what we'll plug it in as is, again, it's going to be that difference in the sigmas, so delta sigma m perhaps, except I got that order wrong. We want to put the run on top, so delta, the change in tau, divided by the change in sigma m, right? That's what it's going to be. And we want to keep that because that angle means something significant. And I'll talk about that in a little bit, but first let me finish writing this equation out just so you can see the parallels, right? So it'll be, that's a multiplication here, tangent phi times sigma m, and then plus the y-intercept here, and I'll talk about this now. The y-intercept here is what we call C, or the cohesion, which doesn't really happen in practice, right? You're never going to have something. What this is saying is there's zero stress, right? There's zero stress, but there's somehow shears coming through it, right? So this is just saying really the cohesion is in a completely unstressed environment. How much resistance is there to failure in shear, to sliding along that plane? That's really what it's telling us. Again, it's not particularly practical to have a case where you're going to be worried about the cohesion causing you failure because you're in an unstressed environment. But it is a property of rocks that we can test for and record and then use in subsequent modeling. So that's why we really care about it. So there it is. That is a linear equation. That is the Mohr-Coulomb failure criterion for shear failure. And again, thinking of it exclusively in terms of compressive stresses is a little bit dangerous. Mathematically, this equation and the one up here, these will yield the same results, assuming you didn't fudge any numbers, right? You derive them empirically from the same data. They'll give you the same results, right? And ideally, you'd be quite conservative with both of them. But if you're only thinking about this, you might tend to ignore loading situations where you do have to be really concerned about how stresses are reorienting themselves, how shears are making themselves a much bigger issue, right? And that's really what we're concerned with at the end of the day. And as an engineer, as a geologist, as a geotechnical person, you should be thinking about everything that's going on with these stresses. Again, it just goes back to, it's a very fundamental thing. It's important for your understanding. Okay, last thing then, like I said, I'm going to talk a little bit about this internal friction angle, right? And why it's so important, why we bother talking about tangent phi, that angle phi, right? Let's just draw, say this is part of a cylinder, right? And we have some, we'll just do it super exaggerated, right? Some big shear plane that's sitting in there, right? And your shear stresses are going to be acting in these directions. And then, of course, the angle in there, this is phi. This is the friction angle, right? That is the angle that these frictions are acting at to try to keep this rock in place so it doesn't fracture along that plane, right? And you start confining it, and this should become pretty intuitive. Look at this picture, right, where we have a pretty steep phi. This is sigma 3 here. And then I'll just illustrate it the same way, draw a similar cylinder here, and then let's say it's really shallow. Call this phi. That's the same thing. Shears are acting along it like this. And then you have the confining stresses. Now all of a sudden, they're acting much more horizontally. They're not opposing those shears nearly as much. They're basically just acting along the same direction as them. Versus in this case, they're really kind of pushing that plane together and giving it more friction, right? It would be like if you're walking with, or maybe your car would be a better example, right? If you load that thing up, all of a sudden the load is perpendicular to the plane. If you're worried about sliding around on slippery conditions, you maybe put some weight in the trunk or the bed of your truck, and it helps you out, right? Same sort of deal. The more perpendicular you're acting to that sliding surface with your confining stress, the better you're going to be, the more efficient you're going to be at increasing that resistance to failure along that plane. That's the really important point. And then, of course, with anything, we could take it to the extreme and all of a sudden say, well, what if we just had a completely horizontal shear plane? Well, now all of a sudden, you have stresses coming in like this, right? And is that really going to strengthen it at all? No, those stresses are just going to transfer along that plane perfectly. And what you'll see is, if we had this, if tangent of phi, if phi was 0, the tangent of 0 is going to be 0, right? So it's just going to be this flat line. That's what it's going to be. And tau f is always going to be equal to just, it's going to be as strong as that cohesion, right? It's going to be a straight flat line just going across that thing. Okay, that is going to just about do it for this video. In the future, we'll get into, now that we've fully explored this Mohr-Coulomb kind of simple failure criteria understanding, we can get into some slightly more complicated ones, but that are ultimately going to be a little bit better for modeling. As far as their practicality goes, again, a key point to keep in mind is just going to be going back, and maybe I'll circle this one more time. If you're looking for real practical stuff, right, this is rock strength. This is still kind of in the laboratory realm. This is not going to be translated super well into an in situ field environment where you've got so many unknowns, right? So you have to take all of these with that warning. This is not the be all end all, this is the strength. This is where things are safe and when they'll fail. This is a tool that helps us predict as one of many factors in a larger system. But we'll get into a little bit more of these later just because it's so much fun. And again, it is very useful. It's very useful to understand your stress fundamentals before diving into the more, I guess you would call them, brute force kind of dumb industry standards, but anyway, that's enough going on for now. Hopefully you enjoyed it, and yeah, thanks for tuning in.